Okay, so welcome to Math 246. This is a course in mathematical modeling. I am Dr. Hansraj from the Maths Department, mathematical modeling. So I wonder what you think when you hear a phrase like mathematical modeling. Some of the guys here are getting quite excited. It's about modeling. Yeah, it is, but not the modeling that you're thinking of. I'll give you that it is about curves. That much I'll tell you is true. So don't run away too early in the course. But it's not the kind of modeling that you see taking place in a lab. This kind of modeling is, we try to understand real world problems using mathematical equations, mathematical tools. So, I mean, there's certain things that are not absolute. Like if you want to know how did the universe get here, this stage, you can't go and find your grandfather and ask him, tell me what happened. He doesn't know. That was his grandfather, and so on, you go backwards in time. We actually don't know what happened at the beginning, several billion years ago. And now, we then as curious human beings, try to figure out what actually happened. So, what we try to do is try to make a model of stuff that we do know. If we can express the current state of the universe in terms of some equation, then we can try to move that curve backwards. We call that interpolating, going backwards in time, and conjecturing what we think could have been at the start. It's a bit philosophical, and may sometimes, that kind of question may end up in a religious book sometimes. But I can assure you we're not going there. What I'm saying is that sometimes we just don't know all the information. It's not available, you can't do anything about it. But you have to use some kind of a technique to see what you do know, and then you reverse something, either go backwards or you go forwards. You want to advance a model. The model will tell you how this thing is going to, where is it going next? So if you're talking about the universe, people want to know whether the universe will carry on infinitely or will it suddenly crash and will all die out and become extinct. Those are good questions that are worthwhile. It's very far away from our time. But you wonder, as a human being, you wonder why, or what is really happening, what will happen in the future. Like somebody, those guys climb Mount Everest. You know these guys, one guy died recently, it's South African guy. I think his wife was gone back. No, that's Kilimanjaro. Kilimanjaro. It's an African mountain, but it's not as high as Everest. But Everest is the tallest mountain in the world, for these climbers. And then they asked one guy, why do you climb this mountain? You're so stupid, can't you just watch TV on the Saturday at home and rugby and cricket and stuff? Why do you want to climb a mountain? So the answer the guy gave, which was Edmund Hillary and Tenzin Norgay, the first two people to reach the top. He says, I climbed the mountain because it was there. In other words, you see something as a challenge and you try to conquer it. That's the human spirit. You have an obstacle and you think, that's not going to beat me. I'll beat it. So you try to climb it. It's a human thing. So these questions about the universe and stuff, you wonder, does it really matter? I'm not going to be around anyway. Whatever happens, I'm not going to be here. I'm going to be long dead. But as a human, you're curious to find out, hey, how this carries on. If you watch a movie sometimes, in the old days, I don't know if they have it now, you stop watching these TV serials, but sometimes the serial will end on a cliffhanger. You wonder next week what's going to happen. These days, I don't think it happens because I see my kids watching a whole set of serials in one day. How is it possible? There's no fun. When we were young, I remember in the 80s, television had just come to South Africa, 70s. There was a TV serial called Dallas. There was a certain guy shot. Everyone was speculating who shot this guy. We had to wait for the whole week to elapse before it was revealed. And sometimes the series would come to an end. And you still wonder after several months while they're making the next step, what's going to happen to this character. Nowadays, no one really cares because everything is just there. But we just wonder, our mind just tries to figure out what comes next. What do we think is the next logical step? So that's what mathematical modeling is about. When you devise a model, you can either go backwards on it and go forward, but it must be what we call a robust model. So You must have a robust model. In other words, you can advance the model to predict something, or you can go backwards. Example, if you want to know about the universe, which no one was there, you can. That's what you can do to get a sense of what possibly happened at the beginning. And some of the real world problems that we will tackle. I'll just make a few notes here and there, nothing serious. I mean, nobody's going to ask you this in the exam. Name 3 problems that you solve. That's like a Psych 101 exam. That won't happen in maths, I can show you. Some of the real world problems, population dynamics. You see, population is a crucial thing. And this is something that should worry everybody. The world population is about 7 billion now. How much more can it go? How many people can the earth sustain? Or in a country, if you take a small country like South Africa, 50 million people, how much of resources are there to sustain how many people? There may be enough land, but is there enough food? Is there enough water? Is there enough oxygen? So you have limited resources, and that also limits the number of people, the total number of people that can live in that space. What is that number, magic number? We don't know yet. We can find a model, and the model can tell us where population is going and what can happen. In other words, you can't just carry on infinitely. Can you imagine the earth becoming infinitely populated? Or you take let's take a city like Durban. If the population gets uncontrollable, it just carries on increasing. Okay, slowly the borders will increase, the city will get bigger and bigger and bigger, but eventually it will cover the whole space. Now, where are you going to go? Into the sea? So there's a limit to where you can go. But fortunately, there's an interplay between the birth rate, how many people are born, and how many people die, the death rate. And that brings me to the next application here, which is actually I wanted to point out about animal population before that. Let's make a note of animal population. This is also a problem, how many rhinos there are, how the rhinos are being killed off, can they sustain themselves, will they go extinct in the next few years? If you plot a graph of rhinos now, what is it telling us is going to happen in the future? That's mathematical modeling. Okay? And then I was speaking about inflation. In economics. You also get inflation in the theories of the universe. We believe the universe will go into an inflationary phase. Right now we are in an inflationary phase, according to the Hubble Space Telescope and stuff. The universe is expanding, accelerating and expanding, but there was a time when it was contracting or decelerating. The model that we use for the universe is Einstein's equations. Einstein's field equations. That's the area I work in, by the way, in general relativity in the university. The university has got experts in many different disciplines. In the Department of Mathematics, the biggest group of people work in the field of Einstein's equations. And we are the biggest in the Southern Hemisphere. That's why UKZN is number 1 in the mathematical stakes in South Africa. UCT is well below us. Our research output scores are 60% higher than UCT, which you don't know. UCT might be more highly ranked on the international scales, taking all subjects into account. But if you take subject by subject in mathematics, UKZN is number 1. I bet you didn't know that. Some years ago, UCT was number 1, but we displaced them 10 years ago. So the figures I'm giving you are a 10-year stat, not just a flash in the pan 1 year. At one stage, because we had bad management in the university, many of our top staff members left, but we managed to attract people from Princeton and Harvard and stuff. We've got 2 guys who are Cambridge graduates, local people. We've got some high-tech people. You mustn't lose confidence in the university. You just have heard the Vice Chancellor resigning. That's a major blow to us in the academic world, but you as students mustn't lose faith in the institution. Nothing can shake the institution. The institution is too big to be shaken by one event. So you can be proud of the degree you get at the end of your career. So inflation I'm speaking about here is economic inflation. How do you measure inflation? Okay, you guys feel free to talk to me because it's class, small class. The topics here are not so heavily mathematical. Like mathematics, I do, but we. To you, you also find it. What is inflation? What do you understand by inflation? We hear it all the time. We are going to the house. One day you'll be earning a salary, paying rent, paying home loan, and home and stuff. What is your take on inflation? How do they calculate inflation? Like you may find the Reserve Bank governor goes on TV and says inflation is now at 4.79%. Or the ANC will have a policy, inflation must be in the band of 4% or 6%. You may wonder as a student, why is the magic number 4% or 6%? Why can't they just allow it to go slightly higher or slightly lower or bring it right down? Of course, getting it right down is good, but you can't always achieve that. That's the hard part. But letting it go high is a very, very dangerous position. What's the inflation rate right now? Are you only watching TV serials? Are you watching some realistic stuff on TV? What's the inflation percent? I'm listening to all these strikes and so on taking place. Post office says I want 12%, and miners are saying we want 11%, and government is saying 6%. Where are they getting these numbers from? It's based on inflation, CPI, for the customer something index, consumer price index. Yes. So they are saying that the inflation rate is say 6%. We want 2% more than that, or whatever it is. Government is saying, no, we will give you what the inflation rate is. So they use those as benchmarks for negotiation. But how do you determine inflation? You tell me. Go ahead, adults. What is the meaning of 6%? They say 6%. You see, as mathematicians, you guys need to interrogate numbers more carefully. When the weatherman says there's a 30% chance of rain, what does that mean? It's a very airy, fairy number. Your mother will say to you one day, put something warm, 30% chance of rain. But what does it mean? Those numbers must mean something. Coming back to inflation, 6%, say, it's a question of what a basket of goods cost this year, at this time, compared to what it cost last year. If you take, and they have a certain basket of stuff, maybe they'll take maize, meal, petrol price, they might take the cost of bread, or something that's basically everyone needs. Call it a big basket of stuff. They'll check what this basket of stuff cost last year, say, what's the date? July 16. Let's see last year what it cost in that day, and this year what it cost. They'll say, now, in a 1 year span, things are now costing 6% more on average. It may be fuel went up by 17%. It could be the price of, say, maize meal, the main that's the same price. If things add up plus minus and then eventually there's a magic number, we call that the rate of inflation. Now, why should you be careful? How do you model inflation? It's remarkable. In fact, you must read about this. The inflation model is actually what we call an exponential model. If you know an exponential function, you know it goes like that. If you take y equals e to the x, remember y equals e to the x? Of course, there's a negative part here, but we don't want that part there. We want the positive part only. What do you notice about an exponential function? It becomes steep very quickly. The derivative of an exponential function is also an exponential function. What's the derivative of e to the x? E to the x. So the gradient is just as bad as the original function. It's just as steep, becomes just as steep as the original function. That's the only function that behaves in the world, okay? The derivative is itself. So if you take, let's say this is from 0 to 2. At 1, there will be a certain value here. At 2, there will be a value right up there. And if you take 3, it could be high up there. It gets big very quickly. And inflation follows that model. So if you have small variations here, there are huge variations there. The delta Y is substantially bigger than delta X. So if you are a Reserve Bank governor, you don't watch where you're keeping this delta X. The inflation rate can become problematic. That's why it's so important for the Reserve Bank to be very strict fiscal policy. You just can't give everybody an increase of 50% or 100% and just dish out the money all over the place left, right, and center. That's one of the reasons why sometimes the population doesn't know this. They just think, oh, we have a lot of money, let's give ourselves lots of money. Okay, I'm not talking about the stealing that took place, that's a bigger problem, right? But let's assume no one steals. Still you have a problem. Still you have a problem. You have to make sure that the inflation targeting is bound. Oh, let me show you a quick graphic here. Yeah, here's some years ago, the inflation rate in Brazil was over 4,000%. You know what that means? It means stuff that cost 1 rand in July last year, now it's costing 4,000 rand this year in July. Now it's silly, right? So last year stuff cost 1 rand, this year it cost 1 rand 6 cents. You won't complain. I mean, you will carry on. You will complain, but it's manageable. Maybe our salary went up slightly also. But can you imagine going to 4,000%? If you don't believe me, I'm not actually hyping this up. Have a look at this. These are the inflation numbers for the world, some countries. You see Australia, 1.9%, 1.9. The highest ever it was 23.9. When there's economic upheavals, things go out of line, but it's still okay, 23.9. Brazil, check Brazil. It used to be 4.39, but now it was 2.86 at one stage. But the highest it reached was 6,821%. Check that. Crazy. It happened. The Brazilian, what is that thing called? Yeah, not real. Peso. So currency. But in any case, it increased by 6,800%. Now, if you look at the other stable countries, I think Canada 2.2, once again up to 1.6, like Australia. But those are very stable economies. Things don't go terribly wrong there. Germany is a very stable economy, 2.10%. IS was 11%. Those countries are strict with fiscal policy. USA 2.9, 2.8, 23.7 was the highest. UK very stable. Highest ever was 8.5%. Because they are very strict. The exchequer there is very strict with how they manage the money. So the point I'm making is that the inflation, the model is exponential. That's why small aberrations in X give you huge aberrations in Y. That's, you've got to balance that off. Okay, some more applications. I said about the universe and stars. This is what we work on at UKZN. Over the weekend, the minister inaugurated the famous Meerkat. You heard of Meerkat? The big telescope in the Karoo? Meerkat. CAT is Karoo Array Telescope, KAT. There was an original telescope called CAT, KAT, CAT, Afrikaans. Then they made another one, they call it Meerkat. So that was inaugurated over the weekend by the minister. South Africa is a leader in this area of research. That's why I say our Department of Astronomy, Astrophysics, General Relativity, Gravitation, we are quite high-powered compared to the rest of the world. So some of our members of staff are members of the board of SKA, Square Kilometer Array. The Square Kilometer Array is the biggest scientific experiment in the world. And who is hosting it? Us. We are hosting it. So we're not such a dwarf country after all. We've got the funds to create it. We also have the engineering capacity to build the entire structure. And we have the scientific muscle to manage it. We are using international work and labor and stuff, but essentially the stuff is built by us. So you as young people have a very bright future in science available. Sometimes students ask your age, what kind of a career can I look for? What should I do with higher mathematics? But all these things are opening up the game. So at this SKA project, not only do you need engineers to build it, there are technicians that are needed to man the equipment. You need scientists to direct the work. You need scientists to look at the data. Scientists will write papers, devise results, tell us what we are learning from what we are seeing from outer space. Okay, that furthers the knowledge base of humanity. And one of the things about this exploration, like the guy I told you about who climbed Everest, because it was there, on the route to solving these kind of problems of the universe, we developed so many other technologies. And those technologies get used in other things like medicine and firefighting. Like that spacecraft they developed to go to Mars. And they developed this heat-resistant materials. So where do you use that now? The firefighters use it. It might be equipment developed to go to Mars, but the spin off is that because we were forced to think along deeper lines, you see, it prompted us to develop something which we can still actually use. If we didn't start to think deeply about going to Mars, people think it's a stupid experiment to follow anyway. It's so much money. Why go there? And what can you do there? But look at all the things that come around. In trying to solve that problem, you learn so much else, which is actually usable to us here on Earth. Okay, whether it's housing or whatever it is. And then another example I can think of is the Richter scale. What is the Richter scale? Used to measure earthquakes. Yes, exactly. Earthquake, like the Richter scale R is equal to log A over A naught. The A here, this is the amplitude of the seismic wave you were speaking about. And this is a parameter that depends on the distance from the epicenter and other factors. There are certain factors peculiar to certain areas. Like the San Andreas fault in California is quite different from the ground situation in Japan, for example, Tokyo. So there are some other things they factor in. They create this number called A naught. Punch it into this formula log of A over A naught. It'll give you a number which is between 0 and 1. You don't hear of a Richter scale. Earthquake was 37 on the Richter scale. You can only go up to 10. So like a log of 100 is 2. So if you take a Richter scale, an earthquake, so if you take an earthquake of say R equals to 2 versus R equals to say 5, what's the difference in magnitudes? Before you say 3, the answer is not 3. When I say difference, I don't mean subtract 2 of them. How much more destructive is an earthquake of magnitude 5 compared to an earthquake of magnitude 2? How many times? 3 times? 2.5 times? We're talking log scales here. It's like 10 to the 5 versus 10 to the 2. It's like 10 squared versus 10 to the 5. So R equals to 5 is 10 cubed times more destructive. That is 1,000 times. Amazing, eh? But that's because we're using log. Log of 1,000 is only 3. So here, this will be like log of 100 is 2, right? 2 log 10. So that will be this earthquake here. Suppose this number comes out to 100. Then that would be 2. If this number comes out to 10 to the 5, that's 100,000. 100,000. Then this would be 5. It's 10 to the power 5. 5 over 10 is 5. So this is 100,000 versus 10 versus what? 100. 100. It's 1,000 times more. You see how numbers can be misleading. You see 2 and 5, you think, nothing, man. That was 2, that was 5. It's really, it's 2, 5. But it's actually 1,000 times more destructive. That's why I said you as young people need to get a sense of numbers. You should know what the numbers mean. Okay, let's leave this now. Oh yes, what I want to say is that this is about modeling and the kind of problems that are there. But if you talk about an effective model, by the way, there are notes that are uploaded online. That's the notes for the module. You don't have to buy a textbook. You can use textbooks in the library, but basically the notes that we give you are self-contained. So you can just rely upon our notes. You can download them or use them on your devices or whatever. Good enough. We'll try to stick to the structure of the notes, but the problems will not be the same, obviously. The ones that are in the notes, you can read about them. It just adds to your understanding. We are also keeping in sync with our Maritzburg people. So we work together to try to make sure the course is roughly aligned. Although we can do different things inside. But the core content remains the same. So when we speak about an effective model or a robust model, I'll put up the information sheet also. We're still discussing with Maritzburg on the test dates. They haven't said hello yet. So we want to decide the dates because we write tests on the same day and the same tests. So we try to make sure we are consistent. But by the way, as I sent you an email last night, did you get my email? You must check your emails regularly now. Your UK's did an email. It's an official channel of communication with you. So if we say something about what topics to learn for the test, you can't come and tell us after this, no, I wasn't in class, I didn't listen. Now we put it in writing. You're supposed to log into your account. So the world works a lot more differently now. It's a legal statement. When I say something through the website, I mean it, it applies. When there's a decision taken about a test or marks or whatever it is, we put it online. Okay, it becomes like a written declaration. You need to log in all the time. I will also send you regular memos talking to you. I have there's a blog on the website. Many students don't like using it, but you could use it. Blog means when you type something, I can respond, and everybody else can see the response also. And that's good. So one guy can't come and ask me, like in my office, is this an important topic for the exam? Now, why should I tell that guy yes or no just by himself? It's unfair advantage to that person. But if you ask me on the blog and I say something, everyone can see it. That's a good thing about the blog. I can also set up a Facebook page if you like. I did set it up for Maths 3A and all that, but people hardly use it. And then my relatives got upset and actually not my relatives. I got upset because other people were trying to become friends who were my relatives, and I don't allow that. I only have 5 friends. I regret having 4. The other one is my daughter, so it's okay. Yes. So effective model should regain known facts. It should allow for predictions. In other words, you should be able to extrapolate or interpolate, go backwards. And it should be stable, changes. Stable. So if you develop a mathematical model, these are some classical tests. It must satisfy observations, what we know to be true. If you develop a model of the universe, for example, we know the universe is now expanding because experiments have shown it. Hubble Space Telescope, and there's all kinds of other things. There's about 10 tests that have been conducted. So if you develop a mathematical model and your model is actually shrinking, then it's wrong. No, it's supposed to satisfy what we currently know. I mean, if it doesn't work for what we know right now, how do you expect it to work for what we don't know, the time we're not in? So that's the first test. I had this problem here I wanted to pose to you at the beginning, but I forgot about it. To show you the importance of a model. Let's say you are a farmer, you own a farm in the Cape Town area, say you're growing mangoes. And you want to, I mean, you've got big portions of mangoes, not like a mango tree at home. Thousands of trees, producing tons of mangoes every year. And your main market, let's say, is Paris, France. Selling the mangoes there, you get more euros for you. So we don't get the best food in South Africa here. Stuff we get a second place. Because of the export market giving us more money, it's better for us to sell our stuff, quality produce, and get money coming from the economy. So let's say you own such a mango farm and you want to make sure, and you know that, I don't know about mango, but let's say from the time the first fruit appears, it takes 30 days for the mango to reach its optimal quality of eat. The guy in France will eat this mango after 30 days. It's ripe and it's not going to rot away. It's the best quality at that time. And you as a farmer, when do you make the decision to cut the mangoes off the tree? When do you harvest the mangoes? How do you make such a decision? So you know that in 30 days' time, this mango must be consumed with somewhere in Paris. You have to work backwards. You have to ask yourself, how long does it take to get to Paris from, say, Cape Town to Paris? It takes a day. You send it by freight. You send it by ships to part of the rock. You send it by plane, freight planes. It takes overnight, 1 day there. Then it takes time to sort it out in your farm. How many days there? 2 or 3 days there. Then it takes maybe 2 or 3 days to harvest, actually cut the thing off the tree, with actual physical and labor. Now, a few days have been consumed there. There's a certain optimal time. How do you work it out? And which day should you cut it from the tree? You see, optimal, I mean, let's say optimal means the sweetest. And the mango's sugar content is the highest. That's something you can measure. Every day of the mango's life, you go to the tree, poke the mango, extract some of the juice there, put it in your. People with diabetes use glucose or whatever, they measure how much sugar there is in the blood, how many moles per liter or whatever it is. You can have a similar device in the farm. You measure how many moles of sugar there is there. You may find the sugar increasing because the thing is ripening. As it ripens, every day the sugar content gets higher and higher. But does it increase infinitely? Does the mango get infinitely sweet? No, after some time, you find that the sugar content will start to decline. Why? Assuming you just leave it in the tree now forever, long time, just measuring the sugar content only. It will go up to a certain level and then it will decline. Why will it decline? What's happening now? You leave it too long. If you leave the fruit too long, you see what happens. It will rot. It will start the process of fermenting and rotting. After a while, sugar content comes down to zero. Try tasting that mango. It will be black and horrible. But you see the model now. You can develop a model, a graph of the sugar content. It's going up, plateau, the maximum, and comes down. So now you know the maximum is on the day number 30. You follow your model backwards to see when was the sugar, what day should I cut so that, say, 5 days after that, it reaches the highest. You see, the decision can't be taken by, you can't do this decision by, what should I say, fluke. If you fluke it, then you decide, hey, orchard here, 10,000 acres. Let's cut it today. You can't wait. So you cut the mangoes, and then now you send it to France. Those are plants and the stuff you want. What do you do? Just lost a whole crop of mangoes. You got no money. In fact, you lost all your money. So you have to do it scientifically. And those guys work in agricultural science and stuff, in our university, in other places. That's what they do. They measure, when they give you advice on how to manage these crops and stuff. So it's very practical. All right, so now there are many variables. The variables describe the changes. And then we form equations that relate the variables. When we say form equations, we mean use some knowledge and conjecture some equations that work. Okay, let's take an example of modeling rhino population. So the variables might be you want to measure in time. So this is called the independent variables, T. You want to know what's the rhino population at time T, after 10 days or 100 days. N of T will be the number of rhino. How many? What is the population? N naught. This could be N of 0. This is the initial population. And then you might have B, which is the birth rate. D, which is the death rate. And let's say K, which is the difference. B minus D. Population is only going to increase if the birth rate is higher than the death rate. You know the inflation problem I was talking about? In Europe right now, they've got a serious problem. The birth rate, the death rate is too low. People are living just too long. So they're reaching this kind of problem here now. There's the birth rate, and also, they follow the economic policy of having fewer children. So therefore, the birth rate and the death rate are not talking anymore. So now you've got a very aging population. Those people retire at 60 years of age. Now they're made at 63 in the European Union. But they are quite productive people. They have to live for another 40 years. Many of them go up to 90s, 100. And they are, depending on the insurance payouts, pension funds and stuff. And those things, when they were first calculated, were not calculated on those numbers. They were assuming the average person, say, dies at 70. Now the average person is dying at 87. So things have gone off. The model has to be tweaked. So now you see this immigration problem. You know what's happening in Europe? You've got immigrants, and you have this Donald Trump, and he doesn't like Mexicans and what have you. In Europe, they've got the same kind of problem. They've got people coming in from the war-torn areas into Europe. At one stage, they were completely anti-immigration. Now they're pretending as if they're trying to be humanitarian in the way they're treating immigrants. The reality is that they actually need the immigrants because the birth rate and death rate are not talking. They're aging. The population is getting so old, they haven't got people to do the work anymore. The number of people in the workforce is not sufficient to sustain the economies. So how do you increase it? You can't suddenly issue a government statement saying that we want you to produce 5 babies per household. It's not going to help in the near future anyway. So the world is a funny place. What you think is a problem in one direction, there are many dimensions to the puzzle. Okay, so this is the birth rate and so on. What is it talking about? Independent variables. Yeah, these are called the dependent variables. Dependent. They depend on T. Dependent variables. And these are like parameters. Birth rate, death rate, and stuff. So these are parameters. Things that's supposed to stay the same. So this is not an exact science. I hope by now you're picking up that mathematical modeling is not an exact science. Things can go wrong. Like I told you, this European problem of aging. What they thought the thing would be like and what it's now is wrong. So we use differential equations. This shows the relationships between variables. Actually, it shows changes. Changes you can measure. So you can measure how something changed from one position to another position. You know what the initial thing was and what it became. You know how much sugar there was in this day, how much it will be in the next day. You can work out the delta, the change in the amount of something, or what we call the differential or the derivative. Hence, the calculus will become an important tool in mathematical modeling. Right, so we use the derivative. The derivative, as you know, is called the rate of change. It was invented by Sir Isaac Newton and Gottfried Wilhelm Leibniz. dn dt. You know the derivative already. You made it in high school. And in first year, you learned about different types of differentiation, partial derivatives. In second year, tangent spaces and tangent bundles and all kinds of things, maximizing, optimization problems. All these things are going to be relevant here in our discussion, in the work that we're going to do. So I will sometimes use the symbol n dot t. dn dt, we can use dot to say derivative. You may not have used dot much in the previous year, but sometimes to shorten things, you can use n dot for dn dt. So, example of a model. You may have something like this, ddt or dn dt is kn. In other words, dn dt is proportional to n. That is, the change is proportional to the amount or the number. So as the number of a certain species changes, the rate also changes in proportion. That's an assumption. It's an assumption. That's why it gives rise to a certain type of model. So this is a certain type of model. It's known as the exponential model. Can you think of any models that behave that way? Yeah, I can think of one from high school. How many of you guys didn't do physics in high school? Nobody. All of you did physics in high school. Okay. You don't need to go do physics in this course. All the stuff will be done from first principles, but it helps if you have some sense of what is acceleration, velocity, and stuff. But we will define everything from scratch. So even if you didn't do it, it's fine. So the model will be something of the type, it will be a function of n, t, derivatives of n, n dot, n double dot, n triple dot, and so on, equal to 0. That's a differential equation. So the example I can think of here is radioactive decay. This is something you have studied in high school physics. Half-life of an atom or an element. Half-life of an element. Like an element like carbon decays. All elements decay. Example, carbon decays. Decays according to a formula. And the formula is dy dt equals to k times y. It's proportional to the amount of carbon that's remaining. Where is this useful? Where is carbon decay useful? Dating of old objects. You find some bones, you want to know how old it is. You find a skeleton, you want to know how old is the skeleton. You do carbon dating. You see how much of carbon is still remaining because it decayed. What it was when the person was alive, when the person dies, carbon starts to decay. So you find the skeleton several thousand years later and you want to know, okay, how old is the skeleton? Check how much of carbon is left in the skeleton. It's not a direct proportion. It doesn't mean that it's carbon decays by 10% every year. That's not true. That's called a direct proportion. That model doesn't work, we know it. The model that does work is this, where you assume that the proportion of carbon is proportionate to the rate of change. The rate of decay is proportional to how much carbon is remaining. And it's an exponential. So if I have to solve this, let's solve this. Oh, okay, let's not solve it right now. I'll solve it in a few minutes then. Come back to it. Let me just deal with a few aspects before we get to the heavy stuff. Another example here, which I see my colleague in Maritzburg is going to discuss, is if you take the motion of a ball. Motion of a ball dropped. So the question is, how long does it take a ball, let's say of steel, of mass 10 kgs, to drop to the earth 50 meters below? The mass of the ball you'll soon see is irrelevant. So you have a ball and it's falling down to the earth. The distance it has to travel is 50 meters. We want to know what is the time. Now, before you start to think of certain formulas you learned in high school, forget the formulas and try to think of it from scratch. Let's see how we do this like a modeling problem. We would say there's only one force on the ball, and that's gravity. And that is given by F is equal to ma. And if you want, you can write it as m dv dt. What's dv dt? It's a change in the velocity per time. Isn't the acceleration? A is acceleration. Acceleration is a change in velocity. And the velocity is a change in what? Displacement. Distance, you could say. So you can say it's m of ds, d squared, s over ds squared, dt squared. Second derivative. Okay. So now you have to choose direction here. Let's say down. What did I choose here? Okay, say up is positive. I had a different problem here, but I just changed it. Okay, say down is positive. Say down is plus. So you would get the only force here, the acceleration, x double dot, which is d squared s dt squared, is g. This is the acceleration due to gravity. It's about 9.8 meters per square second. The second derivative is g. The first derivative of this will be integrate g in terms of t. It will be gt plus a is a constant. But at highest point, we know that x dot is 0. It's at rest. So no velocity. Therefore, it follows that, so if you put naught here, you're going to get g times naught plus a equal to 0. This will then implies that a is 0. So the model simplifies and becomes x dot equals to gt. Because we know that the highest point is no velocity, the body is at rest. So then this a is constant of integration here is 0. That's the only option that you have. Then if you integrate again, you'll get, I'll do this problem in two ways to get the same answer. X will be equal to integrate gt. What is the integral of t? Isn't it half t squared plus some constant? So that gives you the motion of the ball, the path it takes. Okay, although it's going straight down, but the variation is according to t squared. It's like a parabolic motion. But it reminds you of a ball. If you throw a ball up and it comes down, it follows the parabolic path. Even if the parabolic path is very thin. The t squared tells you it's parabolic. So now you have to solve this equation here in terms of find t using x equals to 50. Okay. All right, now, sorry, I don't want to go into the details of that. That's the basic model. Forget the equations of motion. Another idea. The basic calculations you can do is in the book, in fact. But this is not in the book. We can use the conservation of energy. I'm just saying, to solve the same problem, instead of using the equations of motion, s equals to half gt squared plus d, or whatever, we can then apply the, in fact, the b can be 0. Right? When it reaches the bottom after 50 meters, there's, actually at the top, the distance covered is 0. So the b is 0. Right? So you can solve half gt squared equals to 50 and carry on. So b equal to 0. So half gt squared equals to 50. This means that gt squared equals to 100. T equals to square root of 100 over g. That's going to be the answer. Now, conservation of energy. If you think about another physical principle to help us to model this. Here's a ball, and it's falling down. According to the conservation of energy, the sum of the energy is always a constant. The kinetic EK plus the potential EP is a constant. Always. So if you take the kinetic, which is half mv squared, and the potential energy, which is mgh, this is always a constant. So if you take it at the top, at this point here, that's 50 meters, by the way, EK is 0. No velocity. So energy is simply mgh. At the bottom, EP is 0. The potential energy is 0 because there's no height. So the energy is half mv squared. Everything is kinetic. And now you can equate them because at any given point, the total energy is the same. So you can say half mv squared plus, or we are using down as being negative, depending on the direction. Depending on the direction you use here. Half mv squared is equal to mgh. So this will give you, m will cancel off. You'll get v equals to what? 2gh square root. V is root 2gh. So the velocity doesn't even depend on mass. It doesn't depend on mass. And the time, speed equals the distance over time. Speed, so this is equal to distance over time. I want to know what the time is. The time will be distance over the velocity. It will be 50 over root 2 gh. This will be 50 over root, what is the height? 50. So it will be 100 g. Is this the same as the answer above? You check it out, it's the same thing. Rationalize the denominator and you should get the same answer, unless there's any mistakes. Okay, so let's leave that. What those examples illustrate is that there are sometimes two different ways to model the same problem. I've used their kinematic relations, distance, time, velocity, and stuff, and then I also use energy configuration. Depends how you want to see it. In the deeper mathematical problems involving the universe and stuff, we also have a similar thing. We either can use Einstein's equations, which is postulated by Einstein, or we can use what is called a Lagrangian formulation, using dynamical systems. You can study this in third year. Some common models. This is the part where it becomes now for your exams. The interleading part, the first period was basically selling the topic to you. Now, we start to do some calculation stuff, right? I'll follow the numbering in the book, 1.2.1. Unlimited growth model. Or we can call this exponential. I don't know why the book doesn't have that, but this is called the exponential model. Before I discuss it, just recall, what is the integral of 1 over x dx? Ln x, right? Ln x plus c, plus some constant. I can also call this ln x plus ln of c, some other constant. It's the same thing, it's a constant. C or ln c or root c or c to the 10 or whatever, it's still a constant. If I differentiate it, it will be 0. But the convenience of this is that I can say the integral of 1 over x dx is ln of c1x. Log lowers term is again. When you add logs, you multiply them with this x times x c1x. Now, what about the integral of y dot over y dx? Now, we are saying it's like, oh, what am I writing? Like, what is the integral of 2x over 1 plus x squared dx? Well, the derivative of the denominator is actually the numerator. The derivative of the denominator is 1. It's a little function. Oh, you guys have done this in first year. I expected you to rattle this off. What's the derivative of that? The integral of that? Yes? Isn't it the ln of 1 plus x squared plus c, if you like? Okay. How do we show that? What's the derivative of ln of 1 plus x squared? How do you differentiate log function? Derivative of log is 1 over 1 plus x squared, 1 over x, or 1 over whatever is there, times the derivative of the inner function. What's the derivative of the inner function? 2x. So that 2x finishes up on the top. That's why I said the integral of 2x is ln. The derivative is 1 over the function times the derivative of the function itself. That's what I have here. Integral of y dot over y. The derivative upon the function. What will be the answer there? So, integral of y dot over y. Any function over itself, any derivative over itself with respect to some other variable is always ln y. Ln y. Differentiate it. Check. So what's ddx of ln of y? ddx, not ddy. If I said ddy, it would be 1. ddy is 1 over y. But I'm saying ddx. So in other words, y is a function of x itself. Y has got x's in it. Like this here. This is like the y. It's something in terms of x. So differentiate ln y, it will be 1 over y times the derivative of the inner function. Derivative of y. 1 over the thing times the derivative of the thing. So it's y dot. In other words, y dot over y. So when you have to integrate something where the derivative is the numerator and the function itself is the denominator, then the answer is a log, ln function. Why are you so stunned by this? I thought this was a trivial fact that you guys will easily accept. Anyway, so now coming back, returning to the original problem. What did I say there was that, yeah, the model is let's take this model here. I left this one earlier on. dp dt is, okay, let's say it's proportional to p. It's proportional to p. I had dn dt earlier on, but I can use any less. dp dt is proportional to p. The change in the population is proportional to the population itself. The change is proportional to the increase in the population. Okay, so the change is proportional to population change. Sometimes you say population number, some people say population density, whichever, but you must declare upfront what you're talking about. In other words, the model is dp dt equals to some multiple of p. That's what proportion means. Something times p, twice p, or 3 times p, or 5 times p, or half p. It's proportional. It increases by a certain percentage all the time. Or I can write it as p dot equals to kp. Now switch sides. P dot over p equals to a constant. Integrate that with respect to t. What's the integral of p dot over p? Huh? Integral of a derivative divided by its function. It's a log. It's ln. Ln of p equals to, if you integrate k, it'll be kt plus some constant. Let's call it c1. So if I want to write p, eliminate the ln, it will be e to the kt plus c1. Or I can say e to the kt times e to the c1. Or I can just say c e to the kt, where the c is e to the c1. I can just redefine this e to the c1. I can rename it in c. So the solution of the problem is c e to the kt. Therefore, the population varies as some constant e to the kt. So you can see from this model, if k is more than 0, the population increases without bound. In other words, you'll have a situation like this. P. You plot population versus time. P will be CE to the KT. Here we will say, suppose C is more than 0. If C is negative, then C will be down here. What population can't be 0? So it stands to reason that C must be a positive constant. Now you can see this is now unrealistic. Why is this unrealistic? Why? The population grows infinitely. Because the resources are not unlimited. Sooner or later, food will run out. You just can't have an infinite number of people. There'll come a time when the competition for food gets so intense that people will kill each other, and then eventually the population will stabilize in some way. That's why this is an unrealistic model for population. If k is less than 0, then the population decreases. But then this is also false. We know this is not true. From our observations, because we don't see populations getting smaller. That's why I said a model must satisfy what we know to be true. From what we know, populations are going up. There's no way you can devise a model where things actually go down. So that's going to be totally a false model. In this kind of model here, you have a situation like this. Remember, it'll be like a reverse exponential, e to the minus x, which is going to be false. All right, so this model shows that the population is going to become close to zero at some stage. As time goes on, the population is going to become extinct. People will die off. That's the prediction of this model. That model tells the population grows on infinity. So that's not right. We need to now find a model that is better behaved than that. So we need a more efficient model. This brings us to the model of Verhulst, 1.2.2, the model that has got logistic population growth. So this guy called Verhulst, I don't know who he was. This problem was addressed in 1836 by a certain Verhulst. I don't know if he was a mathematician. Maybe he was. So you see, the thing is that, let me write on a new page here. Okay, so let me write a preamble here. So you have limited resources. These are the variables that govern the model. Let's say time is t. Let's define the variables. P is the population, as before. K is the growth rate. Remember I said it's the difference between the birth rate and the death rate. Let's call it the growth rate. And we have now a new object called N, which will be called carrying capacity. The carrying capacity is the threshold. In other words, what is the ultimate? What's the maximum amount of resources available to the people who give them feed? Well, it could be food, water, and any other resources that are not infinite. So if you lump those together and you get a certain magic number called N, that's known as the carrying capacity. That number tells us that this is how many people the Earth can sustain, or this is how many people that can live in this place, this country, or whatever. That's called the carrying capacity. Now, this is very important when you're controlling rhino population and elephants. You know, sometimes you hear that you have to cull elephants in the north of Natal. Cull means you have to kill some elephants. Why must you kill some elephants? It sounds terrible. Average people, I mean, if you publicize this, there'll be a public outrage. People will actually complain. But why must you do that? Why should you cull some animals every now and then? Because if you go to Shishnui, there's lots of elephants there. One thing you'll never miss seeing is an elephant. There's plenty. But you can't let the elephant populations carry on growing. Eventually what will happen? They'll eat all the food. It will not sustain any more new elephants. New elephants will start to compete with the elephants that are still alive, and they're so numerous that there's no food for all of them. So the rangers have to make sure they keep the elephant numbers in a certain range, according to what the land surface area of Shishu Game Park is. So it's a fine line. You may be familiar with the other problem of where, like rhino poaching in the Kruger National Park, where the population is decreasing so fast. There is enough food, but poachers are killing their poor animals. So then now there's not enough animals to produce new animals. So there the growth rate is declining. The problem there. So this guy Verhulst. So you start with, if you start with this this exponential problem, P dot is equal to Kp. We must modify this. Okay? So we want a certain function. We want a function that, what shall I say, with small populations increases rapidly, but as population gets close to N, the carrying capacity, it must slow down. And in fact, it must become almost like no growth thereafter. The birth rate and death rate should roughly be the same. Okay? That's when the population is like an equilibrium situation, you could say. So, what Verhulst did, he proposed this kind of thing here. Verhulst. He proposed P dot is Kp. Multiply this by 1 minus P over N. He proposed this model here. You have the normal Kp, proportional to the population size, but now we have another multiplier of 1 minus P over N. Now it's quadratic. But you see, when the population is small, very small compared to the carrying capacity, very few people, but lots of food available, then this is almost 1, isn't it? This is like almost 0. Take a small number divided by a big number. If we have 5 elephants and we can sustain 50 million, 5 over 50 million, tiny. So 1 minus that, it won't even tickle this one because it's so small. It will be like 1. In that case, the the exponential problem applies. When there's a small population, this part applies. P dot equals to Kp. So the exponential part lives, is dominant. Now, when the population gets big, gets very close to N, there's now lots of people in one small area. Everyone eating the food out and using the water and using up the air. P is getting close to N. What's happening to P over N? It becomes. So P is very close to N. Like, you can sustain 50 million people, and now you've got 49 million people. So 49 million divided by 50 million, almost 1. In other words, you have like 1 minus 1, which is 0. Hence, the growth rate P dot is 0. That's right. When the competition is so fierce for food and stuff, the birth and growth rate must be the same. So the number of people born and the number of people dying must equal roughly, so that the food that they can last forever. That model then is more efficient. You can see that when P is small, P over N is roughly 0. So P dot equals to Kp. Dominates. When P is close to N, and P over N is roughly 1. So P dot will be equal to Kp, the 1 minus 1 is 0. No growth. That's known as a logistical model. Logistical model. Again, it's still a guess. Right? It's not really absolute. It's a model. It can be wrong. It can have some, it needs to be tweaked in certain ways. The K, for example, small k. What is that magic parameter? It has to be calculated based on observations. Take a few readings of animals and food and stuff, and work out what the K is. So this is an efficient model so far. It's doing the trick that we want. If I were to plot this, right? So you've got population versus time, and here you have let's say this is the carrying capacity N. Carrying capacity N. So when the population is small, so here, small number, you will have an exponential part apply. When the population is big, you should have this thing tapering off there, approaching the carrying capacity. So their birth and growth rate are roughly the same. So it tells you the model is something like that. This is known as sigmoidal shape. It's called a logistic curve. It's like your ogive. What we call a normal distribution. You guys do stats? You did stats 130 or whatever, basic stats. Or even high school, mean, median, mode and stuff. I'm sure you did ogive. Cumulative frequency diagram, blah, blah, blah. Same thing, really. There is some way here, there's a magical number. This is where there's a change in rate. So here it's increasing. Now it slows down. So here it's fast. Over here, it slows down. So there's like a point here. What do you call this in normal calculus? Where it goes from concave up to concave down. A point of inflection. It's like a point of inflection. There is a point of inflection. And when does it take place? What's the time? 10:07. 10:10. Okay, let me just finish one last point. In the next period, I'll derive the equation, but I don't have time to do it today. I'll stop at 10:10. Normally, we're supposed to stop at 10:20, but I robbed you of your break, so I'll pay you back. Oh, by the way, we will have lectures today, tomorrow, and Thursday. Wednesday is a TAT normally. In the first week, we haven't done enough work for a TAT. I'll be using the periods for teaching, a double, because on the Thursday period, I have to go to a meeting in Cape Town. I won't be here. The Friday, there is a period allocated in the timetable. Keep that period available. I won't use it every week. When I'm going to use it, I will tell you in advance so you can plan. But don't now, if you have a clash with some other subject, don't try to capitalize on that period. It's allocated for mathematics, 246. Did you find 5 periods in your calendar? In your timetable, there should be 5. I can show you it's 5. Yeah. Monday, 2nd and 3rd. Tuesday, 7th. Wednesday is the TAT. Thursday, it's a 12:20 period. And Friday is a 3rd period. What I'm saying is that the 3rd period on Friday will not generally be used. We will not have lectures on a Friday. But if suddenly there's a strike or something, we lose one period, then we can use that period to cover up. My job is to make sure we have 4 periods a week. We have 52 lectures in the semester. So if I'm going for a meeting or something somewhere, I will always make it up. You will not be shortchanged of 52 lectures. I'll show you that. Right, so all 52 lectures will be given. But I will tell you in advance when I'm making a change, so you're not disadvantaged. Yeah, I just want to say, the last question is, when is the maximum rate of change? So we've got dp dt is p kp into 1 minus p over n. So when is the maximum? When does it have a maximum? The right-hand side is a function of p, which is kp into 1 minus p over n. It's a quadratic, or it's a parabola in p. So you can write it as Kp minus Kp over n, Kp squared over n. At maximum, as we know, f dash p is 0. Let's differentiate with respect to p. It'll be k minus 2kp over n equal to 0. This means that 2kp over n equal to k. Well, the k cancels off. So it follows that p equals to n over 2. So the max rate of change is when the population is half the carrying capacity. Once you eat up more than half of what you have, then your growth rate will start to slow down. It won't become extinct, but it will come down to a constant basis, asymptotic. Okay? I think we shall stop there. In the next lecture, I'll derive the solution for the logistic equation, even though it's not in the notes, but I don't know why it's messed up. See you tomorrow.